Hi, and welcome again to my Physics Online Video Lecture Supplement series. In today's video, I'm going to begin the second set of lectures in the second course of the introductory physics sequence. So this lecture is basically about electrostatics, and it's going to be covering primarily electric forces and electric fields, and ultimately Coulomb's law and Gauss's law. So, to give a general overview of what I'm going to be doing in this lecture, first, let's think back to the courses that you have taken in Introductory Physics 1, be it a General Physics 1 class, a Physics 1 with Calculus class, or what have you. In such a course, you typically study mass and motion. Just about everything in the course is going to have to do with mass and motion. You study kinematics, which is the description of motion. You study Newton's laws, which are the beginning of the laws that govern force and acceleration and motion, and ultimately lead into such ideas as the conservation of linear momentum. You study energy, which largely ends up being kinetic or potential energy, and in the Physics 1 course, usually those basically mean you have some amount of mass which is in motion, and that's kinetic energy, or you have some amount of mass which is held at a particular point with respect to an equilibrium position or a minimum force position, and that's potential energy. And in particular, of relevance today, we had Newton's law of universal gravitation, and this was the law that was formulated by Newton to basically describe how much force of gravity should exist between a pair of masses and ultimately between a set of masses given their position relative to each other and given how much mass each of the objects has. And transitioning to Physics 2, to a course that is primarily about electricity and magnetism and the laws that govern the interaction of electric charges and charges in motion and so on, we have a law which is called Coulomb's law, and it is very much analogous to Newton's law of universal gravity. And the big difference is that we replace the masses with charge, and we replace the universal gravitation constant with a charge constant, which is called the Coulomb's constant. And in fact, beyond those substitutions, the two equations basically have the same form. With that said, if you want to figure out how much a charge is going to move given a force acting on it, you still have to know how much mass that charge has. Because Newton's second law still applies, we still can write that the sum of forces is the mass times acceleration. Basically what this means is that we use Coulomb's law to determine how much force, then we use Newton's second law to determine how much acceleration. So that's basically the first part of this lecture set. The second part is going to be about electric fields, and electric fields basically give us an alternative way of determining how much force is going to act on a given charge. Rather than using Coulomb's law, we basically can use the total electric field strength at a given location and the direction in which that field is oriented, and then the charge of the particle in order to determine the total force acting on the particle. And then we can use these electric fields to predict a few simple properties of conductors and insulators, certainly more easily than we would use Coulomb's law. And then in the third part, we're going to look at Gauss's law, which is a very powerful tool which we can use to help determine electric field strength. So today's video, I basically just want to do part one of this lecture set, which is about electric charge and electric force. Ultimately, it's going to lead up to Coulomb's law. So before we get to Coulomb's law, it's worth talking about charges and electric forces in general. And the phenomenon of electrical charge and of forces between charge has been observed for thousands of years, quite literally. The first recorded observation that we have is from the Greeks from the year 700 BC, so about 2,700 years ago. And what they did is they took amber and they rubbed it, and they found that it could attract little pieces of straw and feathers and so on. Hold a piece of amber that's been rubbed over a piece of straw, and the piece of straw might stick to it. And if you take another piece of amber which has not been rubbed and you hold it over the piece of straw, the straw doesn't stick to it. And sort of fast forwarding through a couple thousand years worth of basically physics theory, discovery, and observation, the attraction between the rubbed amber and the piece of straw or the feather or so on implies that there's a force between the piece of amber and the straw and the feather and so on. Now, this force very obviously cannot be accounted for by gravity. You can do this simply by going back and using Newton's law of universal gravitation and seeing just how weak the gravitational force between the piece of amber and a piece of straw is compared to, say, the gravitational force between the piece of straw and the earth. You can pick up the piece of straw with this piece of amber, even though the force of attraction between the straw and the earth is much greater than the force of attraction due to gravity of the piece of amber and the piece of straw. And furthermore, the force can't be accounted for by a contact force, because you can actually, if you do it well, if you get enough charge on the piece of straw and or the feather, and also on the piece of amber, what you find is that you can actually hold the piece of amber over the piece of straw, and the piece of straw will sort of jump up to meet the piece of amber. So this is not gravity, and it's not a contact force that basically exhausts all the kinds of forces that we study in a Physics 1 course. So therefore, there must be some new kind of force here. And I should say as a caveat to that, that this new kind of force does actually underlie some of the contact forces that we did study, like the normal force. So electricity itself was not much of a topic of interest per se until around the 18th century, when it became a huge topic of interest. And there's quite a few people in the 18th century who started wanting to really study electricity and try to explain it and explain how it works and how what causes electrical charges and what causes electrical force and so on. And so one of the most famous American scientists of the day was Benjamin Franklin. And what he did was not actually necessarily what's shown in this picture. He didn't necessarily fly a kite into an electrical storm. That's a good way to electrocute yourself. But what he did do that was very important is that he basically discovered that there are two kinds of charge, and these are now conventionally called the positive and the negative charges. And the basic rule that governs the force between these two charges is that like charges repel and opposite charges are going to attract. So that means that if you have a positively charged object and a second positively charged object, they should repel. If you have a negatively charged object and a negatively charged object, they should repel, but if you have one positively charged and one negatively charged object, they should attract. And another thing that they eventually discovered was that lightning is ultimately caused by static electricity building up and discharging. So let's consider a few simple properties that go with charge. For one thing, individual charges are quantized. What that means is that there is some minimum value of charge for which all other charge is an integer multiple. This means that if your minimum charge is, let's call it 1e, then every charge in the universe should be an integer multiple of e. So it can be 1e or 2e or 3e or 4e. It can be 400 billion e. It could be 4 times 10 to the 23e. It cannot be 0.5e. It cannot be 0.3e. And we usually set this integer, e, to be the charge that exists in an electron or a proton. Now there's a semi-exception to this, which is that protons are theorized to be made up of quarks. And a quark basically can have a fractional charge of e. In fact, a proton is thought to be made up of 2 of what are called up quarks and 1 of a down quark. And an up quark has a charge of plus 2/3 e, a down quark has a charge of minus 1/3 e. Now, you may say, okay, well, this breaks that rule that everything is an integer charge of e. And strictly speaking, it does break that rule. It turns out, though, that the rule itself, that charges are quantized, still holds. It's just that we've kind of kicked the rule up the road a little bit so that the quantization is not by 1e but by 1/3 of e. So maybe you could call it a little q and note that an e is equal to 3 little q's. Okay, and then everything else ends up being an integer of q because it's an integer of e. Be that as it may, another important property of charge is that total charge has to be conserved. So it's not created, it's not destroyed, but it can be transferred. Now note that there's no contradiction in saying that charges have plus and minus signs and that total charge is conserved. It's possible that the entire charge of the whole universe is 0. And yet you can have charged objects. The reason for this is that for every object that has a negative charge, there must be some other object that has some positive charge, no matter how minute, in order to balance the total charge. Now, I'm not claiming here that the total charge of the universe actually is 0. That is a little difficult to prove, although in theory it seems to be pretty close to 0. I can't disprove that it's 0, in other words. Now, the basic SI unit that we use to represent charge, and this is the third property, is called the Coulomb. And for the purpose of our lecture today, a Coulomb is equal to one electron charge. The charge of an electron or a proton is 1.602 times 10 to the minus 19 coulombs. So if you invert this number, you get how many electrons do you need to get a charge of -1 coulomb. Or if you invert this number, you get how many protons do you need to get a charge of +1 coulomb. So this is quite a small number for the charge of an electron, or quite a few electrons that make up a coulomb. In a later set of lectures, I'll discuss a more practical operational definition for the Coulomb. So moving on, it's worth noting that there's two basic types of substance with regard to electrical properties. One is the insulator, the other is the conductor. There are also, of course, semiconductors, but a semiconductor basically means that it has electrical properties that are somewhere between a conductor and an insulator. And in fact, they're usually able to be switched between being conductors and insulators. So what's the difference between the conductor and the insulator? Well, in a conductor, you have electrical charges which are able to move freely in response to any electrical force exerted. So this includes most metals, and in particular gold and copper and silver tend to be very good conductors. There's also superconductors, which just basically means that the object is an extremely good conductor. Charges move extremely easily. We will get into that later when we talk about resistance, but that's for another day. Insulators, basically, you could think of this as being the opposite of a conductor. Electrical charges are not able to move very easily in response to electrical force. They tend to stay put. So some insulators include glass and rubber. And we're going to look at two different methods now for charging an object. This is actually two methods of charging a conductor. An insulator, you charge by rubbing it. But for a conductor, how do you charge it? Well, the first method is that you can charge via conduction. And basically what you do is you take a charged insulator and you stick it next to a neutrally charged conductor. Some of the charges move off the surface of the insulator into the conductor, or vice versa for that matter. The second method is via induction, and basically what you do is you get a charged insulator and you use it to transfer charge out of a neutral conductor, which has already been connected to ground. So grounding basically means that the object is connected somehow to the earth. Usually it's by a conducting wire. And the earth itself actually is a virtually limitless reservoir for electrical charge. For our purposes, it's certainly going to end up being limitless. And so basically you either transfer electrons into the earth or you transfer electrons from the earth into the conductor. So let's look at those two methods in a little more depth. First, charging by conduction. So this diagram to the right basically shows the process for charging an insulator, charging a conductor by conduction. So the first step is, maybe I should say the 0th step, is that you have to have a charged insulator. So for example, you place some charge on a piece of rubber. Maybe you get a negative charge on a piece of rubber, and what happens is you start to bring it close to a conductor. Conductor has a bunch of positive charges and a bunch of negative charges that are loosely bound together, and basically when this piece of rubber moves close to the conductor ends up having charge separation. All the charges are able to move easily, so all the positive charge moves close to the piece of rubber, the negative charge moves to the far side of the conductor, or moves away from the piece of rubber. So you have a charge separation that basically looks like this. And then when the piece of rubber is brought into actual contact with the conductor, it transfers a bunch of its electrons to the conductor. So basically all these positive charges that we see here end up sort of combining with negative charges from our piece of rubber. They go away, and so we just have a bunch of negative charges that were sort of pushed to the far side of the conductor. So then you remove the piece of rubber and as a result there's a strong electric force here pushing all the electrons away from here, and so they end up eventually distributing themselves evenly around the surface of your conductor. So now you have a charged conductor. It's negatively charged. The same thing can be made to work in reverse if you have a positively charged insulator. Basically, a positively charged insulator which is brought close to the conductor will tend to draw a lot of electrons near to it, and therefore there will be a large positive charge on the far side of the insulator. When contact is made, some electrons will leave from the conductor to the insulator, and then when the insulator is removed, you'll end up having a bunch of positive charges here and a neutral charge here. So some electrons from here will be pulled until they're evenly distributed, and it will be a positively charged conductor. Okay, so let's look at how charging by induction works. And there's actually going to be two methods here for doing this. We'll look at the first simplest method, and then I'll look at a second method that involves charging without grounding. So this is charging with grounding. And basically what we do is we have, first of all, a conductor which has a neutral charge. So this neutral charge you can see is provided because there's a positive charge and a negative charge, positive, negative, positive, negative. Basically, you have a negative paired with each positive. The net is 0. So then you have an insulating rod and it's charged. It can be either charged negatively or it can be charged positively. In this diagram, it's a negatively charged rod, just as in the previous. So you bring it nearby, and again, just like with the case of charging by conduction, what you see is that the electrons tend to move away from the rod, thereby leaving a few positive charges nearby and a strong negative charge on the far side. Now, the difference here is that we never actually touch the rod to the conductor. Instead, we attach a wire from the conductor to the ground. And this wire is basically, let's say, on the far side of the conductor. So what's that going to do? Well, all these electrons are being pushed as far away from this positively charged rod as they can be. So if you attach a wire out the other end that goes to ground, the electrons will tend to flow through the wire. So then if you remove the grounding wire, you end up left with a conductor which has mostly positive charges left because a lot of the electrons have sort of left it. And granted, there may still be some electrons that have built up on one end that haven't flowed through the wire. In any case, when you remove the rod, the electrons will sort of redistribute, and here you can count there's 4 electrons and a lot more than 4 positive charges. Therefore, this will be a positively charged insulator. If we were to draw it, it will basically it'd be the equivalent of having like a plus, a plus, a plus. Pluses all the way around, and then ignore the minuses and some of the interior plus charges. So that's charging by induction using a grounding wire. It turns out that you can also charge by induction without the grounding wire. Here's how that works. In this case, we have 2 conductors which are placed in contact with each other. No grounding wire, so no charges can flow into the ground, but because they're in contact, charges can flow from this one to this one and vice versa. So here we're bringing this time a positively charged rod near to the pair of conductors. And what that does is it draws electrons to this side of the conductor. And basically pulls them more or less from the other side, so you end up with a net positive charge over here, net negative charge over here. And if you do this and then separate the two conductors from each other, no further charges can be exchanged between them. So if you remove the rod, then this thing's negatively charged, this thing's positively charged. Now the negative charges will then tend to move towards this side, the positive charges toward this side, because these are basically acting like a rod to each other. In any case, what that means is we've now charged this conductor negatively and this charge positively. And this whole process is equivalent to having a single conductor to which we have brought a charged insulator without bringing it in contact, basically induced some polarization. In other words, induced all the negative charges to move to one side and the positive charges to the other, and then cut the thing into two pieces that we then separate. So that's a equivalent method to this method for charging by induction. What I want to look at now is basically what happens if we charge a balloon by rubbing it on a woolly sweater. This is, of course, courtesy of the Colorado physics education team. And what we're going to do here is we're going to move this balloon and we're going to rub it up and down on the fuzzy sweater. And as you can see, the result is that we have sort of pulled all of the negative charges off of the sweater and moved them onto the balloon. So now, of course, the balloon is very strongly attracted to the sweater. But watch what happens if we move this balloon close to the wall. So this is a wall right here. And the wall basically is another insulator. But as we move the balloon closer to the wall, you can see that it basically sort of pushes all the electrons out of its path. So we have mostly positive charges pointing towards this balloon, negative charges on the balloon, positive charges of course on the sweater. So let's start over. I'm going to pull a few negative charges off of the sweater. Now I'm going to pull over towards the wall, and the balloon sticks to the wall. And why is the balloon sticking to the wall? Well, even though the wall's charge stayed neutral, you'll notice that for every charge pair, the positive charge is closer to the balloon than the negative charge, and the balloon is basically negatively charged. Now it turns out that, like with Newton's law, the force between two charges is dependent on the separation between the two charges. So if all the positive charges are closer than all the negative charges to the balloon, and the balloon is negatively charged, it should feel a net attraction to the wall. If I pull a little off the wall, it's going to go back over to the sweater. So if I push to the wall when it's uncharged, there's not much that happens. It does kind of stick because, well, the negatives are still a little bit farther than the positives, and the negatives here are a little closer to these positives. But if I pick up just a little bit of charge here, then I can cause some shifting of the charges on the wall. Pick up a little more charge, can cause a little bigger of a shift. Pick up a lot of charge, as many as I can off of this sweater, then we see all of the electrons sort of scatter away from the balloon. So why does a balloon stick to the wall? Well, it tends to stick again if it's actually charged. And basically how it works is that the balloon is a strong insulator. The wall tends also to be an insulator of sorts. So we bring the balloon close to the wall. The balloon maybe has a positive charge along one surface, equivalent to having a negative charge along this surface, because then the same process is going to happen inside the balloon as happens to the wall. In any case, let's say we have a lot of positive charges along one surface of the balloon. As it's brought near to the wall, the result is going to be that the wall is going to get an induced charge polarization. Polarization basically means that you have a pair of charges, one is negative, one is positive, and they are separated by some distance. And as you see here, the negatives are all pointing in the same direction, the positives are all pointing in the same direction, or the positives are all on the same side, the negatives are all on the same side. So what we have here is an induced polarization in the wall's charge, which acts as if the wall has a bunch of electrons at the surface to attract the protons at the surface of the balloon. And so that's why the balloon is able to stick to the wall. Now, there's no net change in charge for either the balloon or the wall. They both have the same charge that they had before sticking the two together, or very close to it. But there is some polarization. And then as the balloon is moved away from the wall, these molecules will sort of reorient themselves so that they're in random directions. So this is basically an induced charge polarization effect. With that said, let's look at what Coulomb's law itself is all about. So Coulomb basically is another very famous scientist from the 18th century, again, that period when interest in electricity was beginning to pick up. And what Coulomb did is he made a series of experiments which allowed him to make 4 important observations that he was able to eventually formulate into a law. And we've actually talked about most of these observations already. The first observation is that an electric force is directed along a line joining 2 charged particles. Second, the electric force is proportional to the square of the distance between the 2 charged particles. That means that force should look like a bunch of constants divided by r squared. Third, it's proportional to the product of the magnitude of the 2 charges. So that means that force should look like some constants times charge 1 times charge 2. And then fourth, if the 2 charges have the same sign, then it will be repulsive. If they have opposite signs, it should be attractive. So these 4 observations can then be combined into a single law, and that law is Coulomb's law. It has a form very similar to Newton's law for gravitation. Basically, F equals some constant times Q1 times Q2 over r squared times the vector that points between the unit vector, the vector of length 1 that points between charge 1 and charge 2. So in polar form, that might look more like this. This is Ke is what's called the Coulomb's constant. It has a value of 8.9875 and some additional digits times 10 to the 9 Newton meters squared per Coulomb squared. Q represents the charge. Sometimes we use little q's, sometimes we use big Q's. We'll see that a little more later on. Basically, you have charge 1 times charge 2 times this Coulomb's constant divided by the distance separating the 2 squared. Compare that to Newton's law, which would have said the universal gravitational constant times mass 1 times mass 2 divided by the distance between the 2 masses squared. This second term gives the direction. It's basically the direction that points from one charge, the charge on which the force is acting, to the other charge. Away from the other charge. Basically, if these two are negative, then it's repulsive. The force points away from the second charge with respect to the first and away from the first with respect to the second. If they have opposite sign, then the force will point from this charge to this charge or from this charge to this charge. There's an additional constant which I'm not using in this equation called the permittivity of free space. It's given by this number right here. It's epsilon naught. I mention it because Ke, the Coulomb's constant, is 1/4 1 divided by the quantity 4 pi epsilon naught. So 4 pi epsilon naught are all in the denominator of this equation. Epsilon naught is permittivity of free space, will become a little more important later. In fact, as soon as we start doing Gauss's law, we tend to use the permittivity rather than the Coulomb's constant. But by using the Coulomb's constant, we see that it looks very much like Newton's universal law for gravitation. So let's look at a comparison between electric force and gravity. So again, here's Newton's law for universal gravitation. Here's Coulomb's law. And if you look down here at this table, it's going to give the values of the charge and the mass for an electron, a proton, and a neutron. An electron has a negative charge, proton has a positive charge of the same magnitude, a neutron is neutrally charged. And notice that these are times 10 to the minus 19. Then we come look at the mass in kilograms. An electron is times 10 to the minus 31. Proton and neutron times 10 to the minus 27 kilograms. And again, the universal gravitation constant is not necessarily a very big number. That implies that if we're looking at an individual proton and an individual electron, for example, the hydrogen atom, the force due to the Coulomb attraction between the two will be far, far, far greater than the force of attraction due to gravity. If we were just looking at a neutron and some other particle, then the force of gravity is the thing that actually dominates, because the neutron has a net charge of 0, and so it doesn't really interact much with electric force. Alright, so let's look at a further comparison between electric force and gravity. Again, the force acts along the line between two particles. That's true for both gravity and for the electric force. In this case, however, you can have only an attractive force for masses. So when doing for gravity, the force diagram basically always looks like this, and it's mass and mass. Mass is positive. If we're talking about charges, then you can have a repulsive force in which the arrows point away from the mutual center, or an attractive force in which the force arrows point towards the center. Here are the two constants that are used for the gravitational constant: 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. For the Coulomb's constant, 8.99 times 10 to the plus 9 Newton meters squared per Coulomb squared. And a big difference between electric force and gravity is that charges of opposite signs can screen each other, which basically means they're neutralizing forces on the pair, whereas masses just kind of add together. We can calculate the total force applied to a given charge when there's several charges present using what's called the superposition principle. And the superposition principle is something that also works when talking about waves, and it will work later when we talk about fields as well. And basically the superposition principle says if you want to figure out how much of something there is, figure out what the individual contributions to that thing is, figure out what direction they act in, and then add everything together with direction and magnitude. So in terms of waves, what that looks like is you have a wave, they're traveling towards each other. They're both in the, let's say, positive direction because the string is deflected upwards. As they travel towards each other, you start to get the total wave, if you will. And when they collide, you get what's called interference, and basically, in this case, it's called constructive interference. To get the total height, you basically add the two peak heights together when they're overlapped, and you've got the total peak height. And then if you add any two points on the wave that are overlapped, you get the total height of the wave. And then as they pass through each other, basically you end up with the little wave that started here moving this way, now is here moving this way. The big wave is now moving this way. They don't really totally destroy each other. They don't permanently add together. They just add together for this period when they're overlapping. In terms of electrostatics, we can do this also with the Coulomb's law. You basically find the individual force vector. Let's say you have three different charged particles. You want to find the force on the third particle from the first two. Well, you basically find the force on the third particle from the first. You find the force on the third particle from the second. You add the two forces together as vectors, meaning you have to pay attention to both magnitude and direction. When you've done that, you now have the total force acting on the third particle. And again, not only does this work for electricity and for waves, it actually is going to work on everything from interaction of two photons in light to gravity, how much force gravity applies to an object. So let's go ahead now and do a few examples. So the first example is really a simple computation that we're going to be doing over and over and over again for different particle-particle pairs. The point of this calculation is so that we can compare the relative strengths of gravity and the electric force for some pairs of basically elementary particles within an atom. Proton-proton, neutron-neutron, electron-electron, proton-electron, proton-neutron, electron-neutron. All right, in order to help us with this calculation, I've basically pasted the table that we used from earlier in this lecture. This was table 2.1.1 in this lecture, which has the charge and mass for each of these particles that we're interested in. And again, remember that the separation distance between the two is basically 1 nanometer. So R equals 1.00 nanometer. And if you've forgotten your prefixes, 1 nanometer is the same as 10 to the minus 9 meters. Okay, and while I'm at it, I'm going to go ahead and write out my two constants. The gravitational constant, 6.67 times 10 to the minus 11 Newton dot meters squared per kilogram squared, and then the Coulomb constant, which is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. All right, so let's go ahead and start with proton-proton. So we'll abbreviate that as P-P. So for the gravity, force of gravity in this case, really we're interested here in the magnitudes, not so much the direction. The direction we know because it's both positive, should be repulsive as respect to the electric force, and it should be attractive because it's mass as regards gravity. So this one, negative G m1 m2 over r squared. Basically, what this is going to give us is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times the mass for each proton, 1.67 times 10 to the minus 27 kilograms, and again 1.67 times 10 to the minus 27 kilograms, and all of that is going to be divided by the distance that's separating them squared. So that's 1.00 times 10 to the minus 9 meters, and this quantity gets squared. So that gives us a force of gravity of 1.86 times 10 to the minus 44 newtons. So that's the gravitational force approximately between two protons, which are separated by 1 nanometer. If we want to figure out what the electric force between the two is, we use Ke times Q1 times Q2 over R squared. So that's going to give us 8.99 times 10 to the 9th Newton meters squared per Coulomb squared times the charge for each proton. So 1.60 times 10 to the minus 19 coulombs times another 1.60 times 10 to the minus 19 coulombs. And then all of that is going to be divided by the separation distance. So again, 1.00 times 10 to the 9 meters quantity squared. So we get that the electric force is approximately 2.30 times 10 to the minus 10th newtons. So that's a pretty dramatic difference from the gravitational force that we calculated above. This is times 10 to the minus 10, this is times 10 to the minus 44. That's quite a few orders of magnitude greater for this one as compared to this one. Okay, so next we do for neutron, and the neutron actually has very nearly the same mass as the proton. So neutron, proton, if we took it out a couple more digits we'd notice a difference, but with only 3 significant figures, basically same mass. So we should get the same calculation for the force of gravity here. So again, that was 1.8 6 times 10 to the minus 44 newtons. For the electric force, though, we have to use the charge of a neutron, and it has a charge of 0, so the electric force between two neutrons should be 0. So in this case, the gravitational force is the greater. Alright, so last but not least, let's look at the electron and electron. So for gravity, we got to use the mass of the electrons, 9.11 times 10 to the minus 31 kilograms, 9.11 times 10 to the minus 31 kilograms. So what that's going to give us is about 8.30 times 10 to the minus 54 newtons. And so now we can do the force between two electrons from their charge. So that means down here we get to put minus 1.60 times 10 to the minus 19, and then again 1.60 times 10 to the minus 19. So that gives us an electric force of, again, 2.3 times 10 to the minus 10 newtons. So this force right here between the two electrons from gravity is 44 whole orders of magnitude lower than this force. That's a 10 followed by 44 zeros, or excuse me, a 1 followed by 44 zeros. So this force is quite a bit stronger than this force. The one that's really interesting, though, is the force between a proton and an electron, because that's basically the force that you get in a basic hydrogen atom. So let's look at that one. In that case, we use the mass of both. So this guy is 1.67 times 10 to the minus 27. And then down here we have the mass of the electron, 9.11 times 10 to the minus 31. So the force of gravity gives us about 1.01 times 10 to the minus 49 newtons. And now let's do for the electron and the proton, and again we're going to get the same magnitude as between an electron and an electron, and the same as between a proton and a proton, 2.3 times 10 to the minus 10. This number basically is about 2 times 10 to the 39 times bigger than this number. So let's write that out. That is this many times. This one is this many times bigger than this one, approximately. That's quite a few zeros. You can count them. There's 39 there. Alright, I'm going to go slightly out of order now by looking at the electron and neutron pair, because the gravity force basically is unchanged if we're sticking with three significant figures. So neutron mass, electron mass, do the calculation, you get something like this. For the forces part, for the electric forces part, the neutron has a charge of 0, and so you get 0 here. So gravity force is a little bigger for electron-neutron than for the electric force. So last but not least, what about the proton-neutron? So gravity force, we need the mass of the neutron, we need the mass of the proton. So that's this number, and therefore the force between the two, again, about 1.86 times 10 to the minus 44 newtons. And for the electric force, again, the neutron has a charge of 0, so you get a force of 0. So as long as we're dealing with a neutron and something else, the gravitational force is greater, but it's a pretty small force. If we're dealing with two charged particles, electron, 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 proton, or proton, proton, then the electric force is far, far greater. All right, let's look at a second example. This one is to look at the superposition principle. So we place three charged particles in a cluster like this. This basically looks like an equilateral triangle, side length of 1 meter, charges 1 coulomb, 1 coulomb, 1 coulomb, and minus 0.1 millicoulombs in the middle. And so we want to know what's the total charge on this, we'll call it a test charge. Here's our configuration of charges, and basically they're in an equilateral triangle, so we can write that there's a distance L separating any two of the charges that are in the corners of the triangle, bearing in mind, of course, that L is 1.00 meters. And the distance that we really need to know is the distance between any given charge on the corner and the charge in the middle, which should be also the same distance r. So what we need to do is solve for r. To do that, we can use a little bit of geometry. So I'm going to redraw my equilateral triangle down here in a less cluttered fashion. And what I'm going to do is bisect it. So this distance is L. If I bisect it, then I should have a pair of right triangles, each with a length L over 2. And geometrically, these two angles must be equal. So we can either use the fact that this is a triangle with L and L over 2, that's a right triangle, or the fact that they have to add to 60. Either way, we find that this angle right here is a 30-degree angle. So that's step 1. Step 2 is to recognize that we have this little dot here that's in the center, and we're going to call this distance r because that's what it is in this diagram. We're also going to draw a right triangle by choosing this distance h, which is going to be equivalent to this distance h, such that we now have a new 30, 60, 90 triangle. And that new 30, 60, 90 triangle has a right angle here, has a hypotenuse of r. It's bisecting this thing, so this is L over 2, just like this is L over 2. So 30 degrees would be here. This is L over 2. And so basically cosine of 30 degrees should be adjacent over hypotenuse. So that's L over 2 divided by r. So what all of this is telling us is that r should be equal to L divided by 2 times the cosine of 30 degrees. and that gets us a value of R approximately 0.577 meters. Okay, so that's the first piece of information that we need to solve this question. Now, before we get the second piece of information, it might be worth double checking this value to make sure that it, at least at a glance, makes sense. One way of doing that is noting that if I were to drag this charge down here to the middle of this line between them, that this distance right here has to be less than R, and it's probably not going to be dramatically less than R. This, at least the placement of these dots, is actually more or less to scale. Well, this is midway between these 2 points, so that means that it is 0.5 meters, and we found that R is 0.577 meters. So at a glance, this seems like a reasonable solution geometrically to our value for R. Okay, now we're going to move on to actually calculating the force between pairs of charges. So since the distance is the same in all cases, that means that the magnitude of the force should be the same in all cases. So the magnitude is going to be given by the Coulomb's constant times the charges, the product of the two charges, divided by the distance between them squared. So that basically is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared times the product of the two charges. So in this case we have 1.00 Coulomb times 1.00 by 10 to the minus 4 coulombs, because this is 0.1 millicoulomb. And again, we're not too concerned with the sign. I'll go ahead and put it in there anyway, but we're not really too concerned with it right now because we're just looking at magnitudes. I'll put in a direction in a minute because we have different directions for each of these charges. So, and then the R squared we found in the previous step was 0.577 meters. So square that. This means that the magnitude of the force for each of these acting on this one is going to be about 2.7 times, I guess it's 10 to the 10 to the plus 6 newtons. So that gives us a magnitude of force between each of these charges and this charge in the middle. What we wanted to know, though, is what's the total force acting on this charge in the middle. So now we have to figure out what the direction of each of these is. Basically, the direction is that this is being pulled towards this one, it's being pulled toward this one, it's being pulled towards this one. So now we got to go back and figure out what directions those would be. So let's call this one number 1, and we'll just go counterclockwise. Here's 2, here's 3. So we'll therefore call these forces F1, F2, and F3. So F1 is basically going to be written as basically Fe comma theta 1. And so what that looks like basically is 2.70 times 10 to the 6 newtons, comma, and it's actually straight up, so 90 degrees. Okay, so that one's probably the easy one. F2 is going to be Fe comma theta 2, and again 2.70 times 10 to the 6 newtons, comma, we got to figure out what direction this thing is acting in. So one way of doing that is by drawing this dotted line and this dotted line to represent our x and y axis. So here's x, here's y. So we basically need to figure out what this angle is, and once we've done that, we really will have also figured out what this angle right here is. So how can we do that? Well, we can look at this triangle here and see that this is the L over 2 part, this is R, so R, L over 2. So this right here must be the angle that represents 30 degrees. So that means that this angle also is 30 degrees. And it means that this angle right here is 60 degrees. Okay, so how does that help us? Well, 60 degrees plus theta gives us 90. So this theta must also be 30 degrees. So we'll call this just simply theta. Theta equals 30 degrees. We look here, we see that this is basically 180 degrees. We're taking 30 away from it. We're adding 30 to it. So this is actually the 210 degree direction. So this is 210 degrees. And then F3 should therefore be Fe, theta 3. So that's going to be 2.70 times 10 to the 6 newtons, comma. And so this right here is if we went all the way around, it'd be 360 degrees. We're 30 degrees shy of that, so 330 degrees. And this actually is good news, because a quick double check that we've got our geometry right is that since these are sort of stationed around a right triangle, around an equilateral triangle, that if we were to figure out these relative directions, they should be 120 degrees apart, because this whole thing has symmetry. If we were to rotate the triangle around, so that 3 is here, 1 is here, and 2 is here, for example, we should get all the same numbers. So we know that going all the way around is 360 degrees. We know that it's got to be split 3 ways. That means that there should be 120 degrees separation between the angles. And sure enough, there's 120 degrees separation between the angles. Okay, so that was step 2. Now we need to carry out step 3 in this process, which is that we've got to actually add all these forces together. And to do that, we should convert all of these into Cartesian. So F1 is therefore going to be 0, 2.70 times 10 to the 6 newtons. And we're just going to count up as positive. So this is the positive direction, and this is the positive direction. Okay. F2 and F3 we're going to have to find by, again, using some geometry or some conversions. So looking here once again, this is the actual direction of the force. We want to split it into x's and y's, but we have this nice triangle. We might as well make use of it. So here's the 30 degrees mark. This right here goes with this times the cosine of 30. This goes with this times the sine of 30. So this is basically going to be in the in the x direction, we're going to have the cosine component of this 30 degree thing. So it's going to be minus 2.34 times 10 to the 6 newtons, comma, and then in the y direction we get the sine component. Okay, so that should be something like 1.35 times 10 to the 6th newtons, and it's actually downward, so this thing is negative. This one right here, we're going now in this direction, but again, this is a 30 degree angle. So this is the force, this is the y part, this is the x part. So we actually end up with plus 2.34 times 10 to the 6 newtons, comma, again, minus 1.35 times 10 to the 6th newtons. All right, so that's our conversions. So if we want to add all these up, we basically add the x components, we add the y components. So we're saying, okay, add all these together. So F net should be 0 minus 2.34 times 10 to the 6th plus 2.34 times 10 to the 6th. So that part obviously should be a 0, comma, 2.7 times 10 to the 6th minus 1.35 times 10 to the 6th leaves me with 1.35 times 10 to the 6th. Then we're subtracting another 1.35 times 10 to the 6th. So this one gives me 0, 0. So that actually means that the net force is 0 newtons. So that is the net force that acts upon this test charge when we have an even distribution of charges around it. And that's something that's important. We'll look at it a little more when talking about conductors and again about Gauss's law. All right, so let's go ahead and look at one more example. This one is an example of what's called charge shielding. And basically what we have here is a line of alternating charges, plus 1 Coulomb, minus 2.5 Coulombs, plus 1 Coulomb. And they're all separated by 1 meter apart. And it should be evident that the net force acting on this particle and the net force acting on this particle should be the same, because they're both the same distance apart from this one, and they're obviously the same distance apart from each other. And from the previous problem, the previous example's calculation, we can see that the force on this one should be 0, basically because this guy and this guy are on exact opposite sides, exact same distance away, and they're the exact same charge. So this one pulls with a force of 1 Coulomb times minus 0.25 times this divided by a meter squared in this direction, and this with the same force in this direction, so they should add to 0. But let's calculate what the force is acting on this particle, because that's a more interesting calculation. Okay, so basically we want to know what is the force on this particle. And we'll take this distance, or we'll find the force from this one, then we'll find the force from this one, we'll add them together. We'll take this distance to be R1. This distance is also equal to R1, so the total distance would be 2R1. So let's call this particle 1, this particle 2, this particle 3. So F net is basically going to be F12, the force on 1 due to 2, plus F13, force on 1 due to particle 3. So F12 is going to be KE Q1 Q2 over R1 squared, or R12 maybe is a better thing to call it. So this is also equal to R12. The total distance right here is 2R12 to get over to this guy. Okay, so this is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared times 1.00 Coulomb times 0.25 Coulombs divided by a meter squared. Okay, so basically what we get is 8.99 times 0.25, which is about 2.25. So we'll call it 2.25 times 10 to the 9 newtons. Okay, and which direction is that acting? Well, it's acting from left to right. So we'll call that direction the positive direction. Okay, and F13 is basically KE Q1 Q3 over R13 squared, which is basically 8.99 times 10 to the 9 Newton meters squared per Coulomb squared times 1.00 coulombs times 1.00 coulombs, because now we're using this charge, and the distance is twice as much, so 2.00 meters quantity squared. And so this guy right here, when you plug it all in, gives us again about 2.25 times 10 to the 9 newtons. But now it's a repulsive force. It's in this direction. It's a minus. So if you add those two together, you can see that they have the same magnitude. They're in opposite directions. That means that the net force acting on this particle is 0. Also means the net force acting on this particle is 0, because we can reverse everything and we'll get 0 again. So basically, these two particles are being shielded from each other by this one, and similarly, they are basically neutralizing each other's forces on this particle, and therefore this system actually happens to be in complete equilibrium. So that is our introduction, therefore, to the topics of charges and Coulomb's law and the beginnings of electrostatics. And we will continue in the next lecture set by looking at what's called electric fields. But for now, that's the end of today's lecture. So thanks for watching, and I hope that you found this video helpful.